Hello, everyone. Thank you for joining this talk. My name is Malek, and I am from the University of Maryland, College Park. In this session, I'll be discussing the water uptake of atmospheric organosulfates at sub- and supersaturated conditions. This work was in collaboration with the Guangzhou Institute of Geochemistry, and you can find our recently published manuscript in Atmospheric Chemistry and Physics Journal using the QR code on the top right. As the title of this presentation suggests, I'll be talking about organosulfate secondary organic aerosols. Organosulfate SOAs have been receiving major attention in the last decade due to their heavy presence in the atmosphere. It has been roughly estimated that they make up about 30% of the total mass of organic aerosols. However, many modeling studies have shown that SOA concentration on the global scale are significantly underestimated, and that this number could be even higher. Organosulfates have been discovered to be formed from a wide variety of mechanisms in the atmosphere. Here, however, I present to you a classical pathway that remains to be a major source of organosulfates. Looking at the image to the right, they can form from volatile organic compounds like isoprene and monoterpene aerosols emitted from trees, reacting with pollutants from fuel emissions such as sulfates, NOx, and sulfur dioxide. The interest within the atmospheric community on these organosulfate SOA is due to their potential impact on climate change. Like many atmospheric aerosols, organosulfates affect Earth's radiative budget directly by scattering or absorbing solar radiation from the sun, or indirectly by acting as cloud condensation nuclei and forming clouds. While it is known that these organosulfates affect climate change, the magnitude and mechanism on radiative forcing remains unknown, and major uncertainty still persists. As a result, atmospheric scientists has put an effort to study these atmospheric particles, and our study aims to reduce radiative forcing uncertainty by studying the water uptake of relevant organosulfate SOAs. Here, we explore three relevant and abundant organosulfate chemicals that vary in length of their carbon chain. Moving on, I'll be referring to them using their abbreviated name that is shown below each structure. The water uptake of these chemicals were then studied under subsaturated condition in the range of 5 to 90% relative humidity. Specifically speaking, two techniques, namely vapor sorption analyzer and hygroscopicity tandem differential mobility analyzer, was used to measure water uptake under subsaturated condition. In addition, the water uptake was also examined under supersaturated condition in the range of 0.4 to 1.1%. using a cloud condensation nuclei counter. While previous studies have investigated the water uptake of methyl OS and ethyl OS using HTDMA, no previous literature has measured water uptake at subsaturated and supersaturated condition using three complementary techniques. I will start with our vapor sorption analyzer results. Here, the figure to the right shows the mass growth factor versus relative humidity for all three chemicals. For methyl OS, which is represented by the black squares, we see that it begins to deliquesce between 40 to 50% RH. As for ethyl OS, it deliquesces between 60 to 70%. And lastly, we see that octyl OS deliquesces between 80 to 90%. To compare the mass growth factor at 90% relative humidity, from the graph we see that methyl OS has the highest mass growth factor with 3.65, followed by ethyl OS with 3.58, and then octyl OS with 1.59, indicating that water affinity increases with decreasing hydrocarbon chain. Our second key finding shows that all the chemicals exhibit continuous hygroscopic growth using the HTDMA. Here, the figure shows the hygroscopic growth factor versus relative humidity. The markers represent this work's experimental data, while solid lines represents a theoretical model that relates hygroscopic growth factor with relative humidity. Finally, the dotted lines represents data from sodium ethyl sulfate and sodium methyl sulfate obtained from a study by Asa-Awuku et al. The continuous hygroscopic growth for all three chemicals that is evident in this figure is attributed to the amorphous state of the particles. allowing them to uptake water at a relatively low percent RH. Comparing our methyl OS and ethyl OS growth data with data from SLR study, we see that they agree well with only 9% difference, which can be explained by uncertainty within the HTDMA setup. To our knowledge, no previous study has explored the hygroscopicity of octyl OS. Here, we report the growth factor at varying percent RH. Looking at the hygroscopic growth factor at 90% relative humidity, we see that methyl OS has the highest growth factor with 1.83, followed by ethyl OS with 1.79, and then octyl OS with 1.21, indicating once again that water affinity increases with decreasing hydrocarbon chain. The CCN activity was then investigated for these chemicals using a cloud condensation nuclei counter, and our data shows that all three chemicals exhibit CCN activity but at varying degrees. Here, as you can see in the figure, we report the kappa hygroscopicity value for each chemical. Each marker point here represents an average of more than 10 data points obtained at 4 different supersaturations. Looking at the trend, we see that it is similar to the previous trends we have observed, in that the water uptake increases with decreasing hydrocarbon chain. This suggests that the addition of hydrocarbon functional group to OS reduces water uptake. Lastly, we compared the water uptake obtained from HTDMA growth factor and kappa from CCN for the pure organosulfate compounds, and also for internal mixture of organosulfate and ammonium sulfate in a 1:5 mass ratio. This figure compares the CCN kappa and growth factor kappa for each of the system. First thing we see is that there is no difference between growth factor kappa and CCN kappa for the internally mixed systems. Second, we see that for the pure methyl OS and ethyl OS, growth factor kappa is bigger than CCN kappa, but only with a relative difference of less than 25%. This can be attributed to the uncertainty that is associated with kappa calculations. And finally, we see that for octyl OS, the kappa CCN is 2.4 times greater than kappa GF. This is due to the solubility limits of octyl OS. Incomplete dissolution under subsaturated condition may lead to underestimation of kappa GF. And with that, I would like to summarize the study. Under subsaturated condition, using a vapor absorption analyzer, all chemicals were found to deliquesce, however, at varying RH values. Results from the HTDMA shows that all 3 chemicals were found to exhibit continuous hygroscopic growth as a function of RH. As for under supersaturated condition using the CCNC, we found that all the chemicals exhibited CCNC activity but at varying degrees. And that when comparing the kappa CCN and kappa obtained from growth factor for each chemical, we see that for methyl OS and ethyl OS, both kappas agree within uncertainty. While octyl sulfate, we observe kappa CCN to be much greater than kappa GF. Lastly, all techniques show that water uptake increases with decreasing hydrocarbon chain. I would like to thank my advisor, Dr. Asa-Awuku, for her guidance and support through this project. I would also like to thank my partner, Patricia, and all our collaborators in Gonzu Institute of Geochemistry. Finally, I would like to thank AAAR organizers for holding this conference and for giving me the opportunity to present our findings. Please feel free to connect with me via the contact information provided below. Thank you so much for listening.